We are honored and privileged to have Mathias Wien, the convener of AG5, today in our meeting. He's going to give us some details of what AG5 is doing these days, and how it works and what's its mission and all the nitty-gritty things about AG5. So we're all looking forward to hearing those from Mathias. For introduction, Mathias earned his diploma and PhD or equivalent of PhD from RWTH Aachen in Germany in 2004 for his PhD, and he became an independent scientist in visual media communication in 2018. His focus is on image and video processing, compression, and quality assessment. And since 2020, he has become the convener of AG5, which is responsible for quality assessment, special video quality assessment, I have to say, for different MPEG projects. And since he has put on that hat, all of a sudden, field drastically from just doing the conventional 2D video quality assessment now to for immersive video coding and for AI-based video coding. I guess we're gonna be hearing from Mathias on what are the new challenges in those areas too. Mathias has been an active participant for many years in MPEG, different MPEG projects, participated in development of issue 64, ABC, HEVC, BVC, and beyond. And also he has authored or co-authored more than 70 scientific papers, and he authored a book on HEVC, and he has several patents in those areas. So with that introduction, the floor is yours, Mathias.
Okay, thank you so much. So, welcome to my talk. I'm very happy that you invited me, and I think it's a good chance to reach out to you and your experts in the area so that we can have an understanding of what's going on in video quality assessments in MPEG. I made a brief outline for the talk. I will briefly present the structure of MPEG as it is of now, because MPEG as such is not just one group anymore, as you will see. I think it's helpful if I just spend a minute on that. And then we will look at tasks basically that are covered by my advisory group, which I structure a little bit along, a little bit along the lines of what's really going on. So we have calls for proposals, we have verification test activities, and then we have activities which are, let's say, in the surrounding of that, preparing and contributing to standardization work. For example, for those modalities VQA was talking about. Okay, so this is the structure that was done in July 2020, and it's what has been MPEG, which was working group 11 in SC29. Now has been split into 10 groups, which is the 7 working groups and 3 advisory groups. And I'm just highlighting those here. And on the left, you see the set of conveners who have been in charge. And they have just been re-elected for the next term from January 24 on. With one change, we will have a replacement for Scala, who stepped down as a convener, and will then will be replaced. Okay, and so you see we have those working groups, the 7 working groups, and quite many of them are working with visual media. Right? So we have MPEG video coding, MPEG joint video coding teams with ITTC. Those 2 are basically JVET, this is WG5, this is the most classic one, jointly with the ITU groups, and MPEG video is let's say the classic group. That's the group that emerged from those who already did MPEG 1. So it's a big, long transition. But also MPEG coding of 3D graphics, and now it's also haptics. Has a lot of things that are concerned with stuff that we do in our advisory group. We find our advisory group down here. Okay. Quickly on the roadmap, why it's important to have this this advisory group. If you just look at what's going on, so the first one here is audio, but then we have massive video coding. Yeah, so MPEG massive video. This is something where you have to determine the quality. Dynamic mesh compression, that's also something that renders to a visual system, so we need to be on that one. The geometry PCC is a little bit less. It depends a bit on what kind of data that is. And this is also like later and stuff like that, where maybe no visual assessment is required, but just for this call for proposals, which is currently being prepared, it seems to be happening, right? LiDAR also is something that where we have to think if that's needed. If you look at the other ones, systems and tools and beyond media is something where we are not so much involved with, but with the explorations, you see the lenslets, you see here neural network-based video compression that's opening a total new scope of what should be done. The explorations towards a potential successor of VVC, AI-based coding also, there's a lot of aspects there. Including changes of artifacts that are produced by the systems which are under development or under investigations, and so this motivates a lot of work that we have in the advisory group. If we briefly review the terms of reference for 85, obviously it's about assessment of video quality. So this is for new technologies, at the beginning of the standardization project, that's basically the end of an evaluation phase. Contribution to call for proposals, we would see examples of how that works for new work items. Contributing in the subjective quality evaluation, but also in objective quality metrics for the assessment of visual coding technologies. So, for example, CFEs or CFPs. Test material for the CFP. So there's a whole lot of aspects. This one is very important. So there's the procedures to evaluate the visual quality on submissions to a CFP. We'll talk about that a bit. And but also, or in general, making such tests conclusive and making this usable for the standardization process. This is something that's really driving us in many aspects of work that we do. Right? Then the next big step is the verification testing, which is basically mentioned in this part in this bullet, maintaining of test material which is suitable, and then also developing guidelines for installation of test laboratories, but also we also have guidelines for the processes that we have, and of course we want to reach out to other standardization organizations which are in the fields. In terms of organizations, how are we structured? The advisory group is not super large. There's a lot of overlaps with the working groups that are in there. But I gathered a group of chairs that we call focus groups. So we have basically one focus group on standard standard resolution. You may have high definition video, HDR. Then we have 360-degree. Which is maybe the focus here is about to change a bit anti-aggressive video coding. So we are trying to cover the most prominent modalities. We don't have a specific denomination for a chair towards something like AI, but it's likely that we might rename this area here sometimes. Okay. In terms of structure, we also install ad hoc groups. Those are the ones which are currently active. We have one joint ad hoc group, which is on interactive testing of visual volumetric data. That's quite interesting because so far the processes that we did with respect to MIV, so MPEG immersive video, or with part clouds, or with the meshes, we always went down, or we went back to a relatively conventional evaluation method. And the reason is that those methods are well understood, reproducible, and people can accept the outcome. And so whenever we introduce a new testing method, we need to make sure that this is a method which is accepted, so that the results are also supported by the consensus of the group. And that's an interesting aspect for this purpose. So this is a new activity that we just had, and I'm really happy that we're doing this. And we have an ad hoc group on quality metrics for 2D video that exists already a little bit longer. We have had some focus on learning metrics, or also metrics for learned material for learned compression tools. So then the last ad hoc group that we have is the ad hoc group on guidelines for subjective visual quality evaluation. That's basically maintaining the guideline documents that we have. There are two, one for verification tests and one for not actually. We will come to those a little bit later. Okay, so that's the organizational parts. Now let's dig into, I covered the areas as I mentioned, so CFP, verification test, and going to some more activities that we have. Maybe just from the perspectives that we have here. So when we have a CFP for visual media standardization process, what is the goal there? The goal typically is to find the right starting point for the standardization process. And so what's typically done, we have this call for proposals, and the responses for the call are evaluated. And that's what is called the competitive stage of the standardization process. So the proponents are concurring to try to get the best proposal, and then the question is, what would be the criteria for those proposals? And in order to come to such conclusions, what is essential is the clear definition of the test set, of the encoding constraints, the reporting requirements. So what is needed to be delivered, so that in the end we can draw conclusions. And typically what proponents are asked for, well, algorithm description is somewhat clear. Objective quality metrics, that's something that the performers would do by themselves. And also complexity metrics, so like maybe runtimes, but also numbers of operations, all these kind of things. It depends a bit on the group, which numbers are collected there. And then we would have a formal assessment with one on all laboratories. It depends a bit on the size of the activity, which results in reported mean opinion scores. And I'm just showing here an example for the example CFP that I want to talk about, was to give an idea that things may be quite different from conventional video if you look at that. But the goal is, so we do this objective assessment, and then what we want to achieve is a ranking of the proposals, meaning that we can identify which one would be working best. And so the example, as I just mentioned, will be the CFP for dynamic mesh coding. So that's an example from working group 7. And the CFP was issued in 21, and the evaluation was in April 22. And so since then we have a collaborative standardization phase, meaning that the winning proposal, or the what became the test model, then is refined towards sterilization to be to become an international standard sometime soon. So how does it look like? So in this case, we had two encoder configurations. You see them here. One was random access, the other one was all intra. For each of them, you would have 5 test sequences. You see that we have 4 breakpoints that were to be evaluated. And then the question is, how many submissions do we have? So in this case, we only had 6. That's something that can be relatively easily handled, but maybe more, and then more challenges arise depending on what's going on. And then, so for the evaluation, what we do, or what was agreed on here in this case, first thing is there was this rendering to 2D video, and it was decided to have a neutral background, and then the videos would be evaluated by the native subjects that would be in the test. This was something that was agreed by and also with the WG7 experts, so that's something that we did together. The benefit is that this is something which is very well understood. And so the idea was the proponents were supposed to submit data for those rate points. So as I mentioned, we have those 4 rate points here that would be evaluated visually, and then you have these bit rates that were supposed to be met for those different content items that we have here. And after the submission of the proposals, actually I did a design of camera paths that we would use for evaluation, and those would not be disclosed to the proponents, of course. This was only done when reporting the data, so that the proponents do not know where we would look at their data set. And this is basically to prevent that somebody might optimize the code to maybe just be good looking on the area that is evaluated by the test and potentially saving rate on other areas. And in order to prevent that, such information must not be disclosed, of course. So what was then done was, after deciding the view path, there was a rendering that was actually not done by me, but was done by by people supporting the WJ7 convener. This also was a significant effort. And so we were delivered the video data that would then be evaluated. And we did that by using the very classic and typically used LTS and TSS or TCR evaluation methods using the 11 grade scale. So we're in MPEG, we are pretty much settled on using this scale, and people are very much used to that score. So that's why we typically use that as an evaluation basis. Okay, so we have the DCR and the 11 grade scale, and then we got the results. And now the question is, how do you do that? The method that we applied here was one that we already also applied in VDC, which actually worked on a different scale. So this is just to make that clear. Here you see in the current proposal that we're talking about, we had 6 proposals. In VDC, you had 22 in the SDR category, 12 in HDR, and 12 in 360. So that's a very, very large scale. And so actually, the method has been proven to be effective for any of those scales. And so only the more proposals you have, the more competing proposals you have, the more sensitive or the more complicated maybe the ranking of the proposals may be. And this is actually the core element. So we rely on the confidence interval, the 95% confidence interval that's computed, and then we assume overlapping CIs to indicate proposals that would be considered comparable, and non-overlapping CIs would be considered to be significantly different. And so now that's what is basically done. That's what you see here, and this is what I would like to explain. So we see for each of the rate points, each rate point has a different color. We see a ranking of the proposals by the MOS value. Yeah, and so basically here we have those 6 variants. We have the 5 proposals and the 1 anchor. And then we have a ranking of those in this order, and that's reflected down here. So you see, for example, first point was the proposals are anonymized here. So this is just B, then comes proposal A, then comes proposal F, then C, then E, and then comes D. Right, and in this case, I think E is the anchor. So that would mean now if you read what's shown here, it's illustrated with these 2 blue lines. For example, the best proposal is proposal B here. We have the next proposal, which was proposal A, overlapping with that one. So we would consider those 2 to be the best performing ones in this table. And then we have a drop. So proposal F would be significantly worse than the other 2. And so the overlaps, they're just not overlapping. And then there's drops for the last group, the group of the last 3. And so we do that for the highest rate point, for the second, for the third, and for the lowest rate point. Those are basically the results. And in this case, and actually in the CFP, it was always the case that was proposal B always turned out to be the best one. And you see that this actually happened quite dramatically. So for that proposal, you see the 4 rate points, and apparently there's saturation because those 2 points are not very far apart. Right? So they're basically overlapping. That means that the additional rates from 3 to 4 didn't help too much. But then you see that the proposal, besides the highest rate point, all other points were already significantly better than any of the other proposals. And so that's a very easy thing. And basically, what you can do with these curves, you can try to basically look at that. So, for example, if you like the second one is the proposal A, there's also this point, and then this proposal drops down in here. And if you look closer, you see that for the fourth point, we don't see the A, so they actually are not able to submit something for the lowest rate. Also see the anchor did not submit something for the lowest rate, and that's why you have missing points down here, and those sets are a little bit shorter. And so you can basically have a very good overview of what happens in this case. We have a quite clear winner with this proposal B. That was basically significant for all the for all the sequences, the test cases. So in that case, the CFP was a very clear activity, but that's basically what we typically try to do. And this is also something that we would do, for example, when we change the viewing method to some reasons, but the concept itself, that always, of course, remains the same. Okay, let's come to the next part, which would be verification testing. The typical project that we would have in standardization would be that exploration. There's a CFP, then we have this working draft, commentary draft, final commentary draft international standard process. And after that, basically after the finalization, or maybe also somewhere around this transition, the verification test process would start, which is meant to double check what has been achieved. So the requirements achieved, and specifically as part of those requirements are the compression goals achieved. This is something that's very important because it can be used. Well, since it's public record, it's basically something that can be used to advertise the new scheme to be adopted by industry for their products. So having this is a very helpful tool as a completion of the standardization process and giving test data at hand that may help decision making in the industry. And the main tasks are that we have to build something which is trustworthy and reliable and usable for this purpose. So what we typically do, we do something which is not, they call the common testing scenario, which means we are not like with common testing conditions that have been used to develop the standard, but we use something apart from that. We specifically use something that would be representing relevant use cases. So like for video coding, it would be like streaming, conversational applications, but also others. And the test sequences, of course, must not be the same that have been used in the development process. The rates, so the quantizer settings, everything would be different. What might not be different, but similar would, for example, be the encoder configuration, because typically the configurations of the common testing conditions kind of reflect very typical scenarios of use cases. So that's something that may be used, but it's still sufficiently different from what has been done in the process, in order to avoid that there would be some bias, for overfitting reasons or something like that. And also, what we typically try to do is that we would have a quality range that's covered that may be a little bit more than what the application needs in order to get a full characterization of the scheme. Right? So if you think of UHD video, we might not go down to very low qualities because we would do something else, we would switch resolutions, whatever. But still, it's interesting to know how the system behaves under adverse conditions, and this is considered to be useful information for the outside world as well. So, since the way or the steps that would be needed for verification testing have been challenged a bit in the starting of AG5, we decided that we would define some guidelines for verification testing, and those are basically, it's a relatively short document, so just 4 pages, where the core elements actually are already captured on the first 2 pages. So it's really a relatively short document, but it makes very clear what we have. So what is the the purpose and the goals of the verification test. What are the procedures? What is the selection criteria for test material? What should be regarded when bit streams or breakpoints are, and then the breakpoints are selected? How the visual test should be conducted, and how the reporting should be done. And all those things are very relevant in order to make this information that's published in the verification test something that's trustworthy, it's reliable, and that's also reproducible. This is something that's very, very helpful if the verification test has the qualities, because it sends a good signal to the outside world. So we should not exaggerate the gains by searching for some sweet spots. Of course, we should also not over critically select material where things don't work, but put something which is meaningful and useful in a fair manner. That's basically the approaches that we try to follow, and that's what we did. We have a bunch of such activities which already have been completed. Just list the parts. There is some of them. So we have the EDC and LCEDC schemes that were kind of inherited for AG5 because they already started before we came to life. The first big one that we did was VVC, and I just have some curves here. You see the curve, the pool curve for the MOS values over bitrate, and for the HEVC test model comparing to the VVC test model. That's HN and HEM. Then the third thing that you see here was the VV-Inc. Open source implementation. That was also part of the game, but for the first purposes, it's just important to look at the orange and the blue curves. What was concluded just beyond the rate savings was something about 40%, which seems to be realistic. And similar results were achieved for HDR and also for 360, where we have some this kind of stuff data. So those are results which are considered to be quite helpful and useful for the advertisement and also the adoption process of the standard in the outside world. One more example would be immersive video. That was the last one that we did, which is also interesting in the sense that we typically do PCR tests, as I mentioned before. Here we decided to go for the ACR with the argument that the ground truth in this case is hard to get because of the influences of the render and so forth. So it was decided to rather go for the absolute category rating, the degradation category rating. Where in DCR, maybe just to remind people who might not know, we would compare the coded version to the original, and then we want to measure the impairment, which means that we know what would be the best thing achievable, and we want to measure how much the coded version diverges from there. And we basically project that to the 11th grade scale. In ACR, we have absolute categorization. We don't have a reference, so the viewers just get the original, they get the coded versions, and they just have the interpretation of the scale, and they shall score everything there. And then, if you want to compare, you basically have the distance between the best reference, what you would get, or the coded versions. And this is actually what you see here. These two examples that I included in the slides. And so the main messages are very easy. So you see the green curve, that would be the performance of the best reference, and then we see different variants. So in the upper case, that's a sequence with natural content, myth, and the geometry only profile, the geometry absent profile of myth, which perform significantly better than the anchor, which was NB HEDC, so multi-view HEDC coding. And you see that you get quite some saturation for those at already at relatively low bit rates compared to what we're looking at, while the geometry absent already reaches overlaps in the confidence intervals as the description. So meaning that the coding process itself would not provide you gains anymore, but what might be possible, and that's something that you see here from the scale, that the rendering process that is used, which would leave some headroom for further improvements. And similarly here, this was a synthetic sequence. We see that we basically get some linear increase into it. Again, here you have quite some substantial gains that are observed. And this is kind of the information that we try to share and try to advertise in the outside world for those tests. Organizationally, maybe that's something that I actually mentioned on the slides. 85 would conduct those tests and will prepare the test scenario together with the working group, then conduct the test and then hand over the data to the working group, who will then produce the output document. That's something that you see down here. So you ask the working group for output document. That's then basically the final report on this activity. What's the version is scalability. We will look at that a little bit, and a testing activity, which is not specifically a verification test, but a mere evaluation for the film grain characteristics. The difference may be subtle, but it's evident. So verification tests are something that would be done for standards, while in the film grain case, there is not a specific standard, but it's an SAI message, and it's a technology that can be added on top of regular standards. So this is something that would not be classified as a verification test in that sense, but rather just a visual evaluation, which is helpful nonetheless. As you know, as you might know, there's a technical report on film grain characteristics being prepared by JDET. This kind of accompanying this activity. Okay, so what's on for multilayer coding? First one category. So for multilayer, we have 4 categories. First one is basically the efficiency of spatial scalability coding. Here the focus is on 1.5 and 2x spatial scalability. And the question is basically to what extent, what is the price for having that kind of scalability? The second one is the so-called quality ladder. That's something that's just streaming a lot. We would have a meaningful combination of resolutions and rate coins, or the rate set, and then, for example, Dash could be used, or any HTTP adaptive streaming methodology could be used to pull data from a server. The latter basically provides the ability to adapt to network conditions and other events that might affect the quality of the transmission. Right, and the scenario here is, or the use cases that scalability may help to serve to save some storage space on specifically what we could call the edge storage. So the CDN, the content delivery network, basically on the last mile when we would push the data to the specific users, where you have to store all the videos that might be called. There, if you use scalability, you can save something. And I think the savings might be around something like 20%, so it's quite significant. Okay, third category would be content layering, where you would might have something like so-called sub-content, so overlays to the video and things like that, which would be supported in a scalable stream. And the benefit of that is that you can support this technology on the video stream level, right? So typically this is a topic that's handled on the systems layer, but if you want to, you can also do that on the elementary stream level. So basically having a scalable video stream that would provide you the version with and without this kind of layering, exploiting thereby the functionality of the multi-scale stream. And the fourth category, this is the one with the least activity so far. That's about dual view coding, which is so specifically like stereo viewing of the 2D video, and which is on the roadmap, but not yet developed so much. Just to give you some insights, currently what's considered our feedback that we have here, we did some expert viewings to settle on bit rates, to settle on or to confirm selection performances, and sometimes this expert viewing, which is basically as a pre-step before we would do a formal evaluation and before finalizing the plan. This is very, very healthy to do because what we, for example, found just at the last meeting in Geneva, that the objective performance, for example, of just upscaling the base layer may look very different from what would be rated subjectively. So this is something that leads to the investigations, because the inspection of the data showed us that the gain of detail by single layer and also scalable version is clearly better than what would be there in the upscaled version, the base layer. But then there are other artifacts that overrule this kind of these gains. So next evaluation step, the next development step will be to tune the coding and such that we don't have that issue anymore in the performance of that. But basically, this is kind of something like the last step before we would run a final round of objective of formal subjective evaluation, and then could produce another verification test report on that. For the second category, the quality letter, this is a work in progress, but just to show you what's on there. So you have a draft table of how things might look like. This is inspired by the HLS screen provided by Apple, which does not yet have the VVC category. And then you have a suggested set of bit rates for VVC. And you see that if you look at the HDR increase, so the relations, it's kind of just trying to propagate what has been done with ITTC now to the bitrate range of what is considered to be useful for VVC. You see on the right here, there's some examples where you have the YPSR, so the Luma analysis for the causal joint sequence, where you have then different breakpoints or different quality metrics on the different resolutions. You see down here the resolutions that are evaluated, and then what we basically try to do is something like a convex hull of the streams to provide you a good coverage of the MOS scores at the optimum bitrate resolution combination for that point. And that's basically what is currently evaluated and investigated. For the content layering third category, this is just an illustration. There was the very nice demo provided in Geneva, which is shown here. So you have basically a small tablet that would be used as a controller. Then you have a streaming device that basically would provide the data using the MMT format, and then there would be a multi-layer VVC decoder, which is then basically controlled by this tablet, and then the output would be rendered to a 4K monitor. And here's just one of the examples of how this content layering might look like. In this case, you see that the base layer covers one video, and then you could activate, or if you activate the second layer, the enhancement layer, then you see that the base layer is actually downscale to a portion of the video, and then there's, in this case, there's some sign language which is added for people who might need that kind of information. And the connection is basically that since DVC allows the enhancement layer also to be smaller than the base layer, by concept, you can basically exploit information in this base layer to have a very cheap representation of this area in the enhancement layer. So overall, you have some benefit in the overall coding cost from this kind of data. And there were other use cases, and if you're interested, you're invited to look up the input contribution AE 285, but there also will be a report being prepared from David that will more formally present those results. For the third game, maybe just to move on, this is actually something which is very different in the way testing may be done. And I think I don't have the main goals. There we only have two categories, maybe just to sum that up. One category would be using film grain technology to achieve better compression performance. The other one would be using film grain synthesis to emulate actual noise in the video stream, and that noise would be sufficiently equivalent to what is the intended noise in the video. So this is specifically important if you consider movie content, big films that would have a certain aesthetic intent in the artificial or actual film grain or film noise that you have in the video. That is something that we would like to bring to the customer, but coding that is very expensive. So removing it, coding without the noise, and then synthesizing it at the receiver side would be a very good thing. And this is basically the intention to study the capabilities of that technology. The film grain on its own is something which is about 20 years old already, and has been there around quite a bit, but so far has not been thoroughly tested in MPEG for these purposes. So in this sense, it's something like a relatively new activity for the standardization committee. It's not so much new technology that's actually considered. It's just that there's film grain technology available also in other schemes that are around, and so the intention to just demonstrate what's possible, for example, with VDC, might have been inspired also by this kind of activities. What have we done so far? We did expert viewing as a trial run to see what's going on towards what's called goal 1. So that's the benefit of film grain tools for compression. And what was tested here was the QP selection for the current set of sequences. You will see what that's about in a minute. The confirmation of what we would use as a lowest QP point, so the best quality, which would just preserve film grain. And then the last thing would be some indicative rate shading checks for the film grain activity. And so since we are talking about depending on what we do, so for the QP selection, we actually went for a DCR method. So you see the viewers would see the original sequence with its noise, and then they see the coded version. And then they are supposed to judge the overall impression. For the lowest QP point, where we are at very high qualities, we decided to go for an A/B comparison, so that we more granularly can decide on which one would be better and which one would be worse. And so the results for those two tests are now shown. So this is first the DCR result, where we see at the very low end, typically we have no or some little benefit, but it's not super significant. If we go to the higher rates, then things might be different. So you can see here for the Duosine, for example, we had some significant benefits at the higher rate points, and then some saturation effects in the upper end. And for the old town cross sequence, you see that there's a clear benefit at the higher rates, with a breakdown if the bit rates become too low. So those are actually very promising results. Currently, what's going on here is the question on what kind of content should we have. So this set, we have crowd run and old town cross, which are both analog video, so digitized by scanning the film. So that's actually original film grain noise, but also overlaid with like film artifacts, which are like scratches and things like that. And the Duosine is a scene that has been captured by a digital camera, and then has some artificial noise. So that's something that needs to be covered as well, because that's basically the way how state-of-the-art video would be produced. And having artificial grain means that also different types would need to be considered. And so there's a lot of discussion currently going on how to evaluate that. We had some contributions in the last meeting, one from Apple, which was very nice, where there would be something like a clean video, and then they promised to provide some versions with different amounts of film grain added so that we could study the effects of the film grain and also the impact on the compression very nicely, because we have something like if you look at it from the coding from the noise perspective, you would have a ground truth that then would have additional noise. So that's very interesting, and we'll continue further. The other aspect that I mentioned was this A/B comparison at the very, very high bit rates. And here, what you see here, this was a A/B comparison with 5 scores that could be given. So you could say that the two are equal. There are the one is better than the other one, or it's clearly better. That was basically the options that you would have. And you see here the comparison of the version without film grain synthesis, so the plain coded version compared to the original. And what you see is that the QP has been chosen such that the viewers rated those to be equivalent. That's basically the message that we have here. While for the second one, where we compare the FGS version against the non-FGS version, you see that you have a slight drop here for the FGS version, but not super significant. So ideally, also those would be rated similarly, because then we would say we are on par. But you can see that, I mean, this is kind of a very optimistic way of testing it. And this is something that you also see from those numbers, where you see that you have a lot of bit rate that can be saved if you just synthesize in this range. But this is not something that we would consider realistic. So the intention is that we would do a next test, maybe where the non-FGS points would have a little loss compared to the FGS, so that we are more conservative in the bit rate savings that we would have here. That's something that would come in the next steps. Okay, then we would go for further activities and topics. And also I see that I'm also eating up a lot of time. The first one is basically, again, a little bit on the testing, what we do. So driven by the pandemic situation that we had, we developed the guidelines for remote expert testing, which we did a lot during the pandemic phase, typically with A/B comparisons, where we wanted to evaluate tools against the anchor. And so this one expert, the one aspect. Since we are now back to presence mode, we can put brackets around the remote and just look at expert viewing, and look at specifically, and that's something that we are too active in investigations on efficient training methods for the viewers, and that's something that's driving me for the purpose during the meetings. We are under very high pressure, and we want to be successful there. Another aspect of that is also, since we are looking at, specifically in those A/B comparisons, we are looking at coding at very subtle differences between schemes. Like, so the proposals typically are not super far away from the anchor. So the question is, how do the objective metrics behave on that? So how well do they recommend the same suggestions as the subjective test? And that's something that we are also working on. And so just giving you some examples without going into details. What typically was done in JVEG, for example, was using a 4-grade scale. So that's a forced choice. Could just say it's better or worse, or it's much better and much worse for the comparison of the anchor and the proposal. And with this, then we would collect those data and do the analysis based on that, typically using a value of ±1 and a value of ±3 for mapping this to a numeric scale. And you see here some results that we had. And for example, in this case, you see that there are some tendencies which might be considered to be clear for most sequences here. For this one, for Tango, it's not so clear for this point, maybe just here for that one. So it's a slight tendency, but it's useful, right? So you can say, okay, so in this case, you have one point where it's actually the scheme's worse, that at the low rate point, so you see here the QP is at 7, that's the higher rate, this low rate that was evaluated. And so the proposal, actually, I even don't currently know which technology that was. That might have been some super resolution. So, but it seems that the technology on average might bring some benefit over the anchor technology. And so this is something that has been done. For the objective metrics, what we then actually did, we look at the results and then throw that against a number of objective metrics that are available. So, like for example, in this document, where we have some classic ones, some learning-based ones, and then we want to know to what extent are those metrics consistent with the subjective results that we have seen. And that's you see here some are less. And that's from those studies we want to derive potential recommendations for metrics for a specific purpose, and that's something that we can actually do actually for any type of metrics, right? And for any type of content. So the only constraints that we need to build up a database sufficiently large to let us allow for some decisions. Talking about the expert viewing that we do that a lot. Typically, as I mentioned, there are quite some constraints on it because we have to be very fast, we have to be very efficient, we should not make some mistakes. And what you see here is some examples. For this was in the Mainz meeting last year. This was earlier in April. We also had a setup in Geneva just in July. Typically using a 65 OLED screen, running driving that with a computer that would be capable of doing stable real-time UHD output at 60 Hertz and 10 bits, and thereby gaining some nice outputs. And then just for this training purpose, speeding that up a bit, this is reports from the Antalya meeting, where we used a modified training method where the users would be allowed to, so that they get a training session, they note their scores, then they would read out those scores on one sequence after the other, so that they get the idea of the distribution of scores that were given. And if there was, if the variation of those numbers was larger than 3, that was the set that we had used for that purpose. Then, without commenting on that, just telling them, okay, so there's a divergence among the opinions. So we just show it again, and everybody for themselves would consider if the previous vote would be appropriate, yes or no. And just by doing that, without exchanging information on where to look, of course, without forcing them to change their mind, just to confirm or to reevaluate what they have, we actually were able to improve the result, or stabilize the result of the test quite a bit. And so what was happening here at the outputs of Antalya was there was actually no failures on preference sequences that were recorded, and just one single value had to be removed from the tests. Those were the results, just to show you that we also had quite nice confidence intervals that came out there. And while the other expert viewing sessions often tend to have larger confidence intervals, here we were way more consistent. But so that's something that we are intending to continue to work on as an efficient method. Then finally, just going on what's going on, we have one activity, as I mentioned, together with WGD4 on making the testing of immersive videos, so visual volumetric data, making this testing of immersive video interactive. We started an activity to develop methods for this purpose, and so that we have a more or the test method would be closely to what actual users of the technology might observe later on, while at the same time we try to get something that's reproducible. And that's the challenge. If you're immersive, there are so many ways where people could look, and it may be very difficult to get a conclusive result if people are looking at totally different parts of a video. So having some guidance is helpful, but at the same time, leaving some freedom is also helpful, which is something that we're going investigate further now. The second one that I wanted to mention is setting up this data set that I talked about earlier for compressed video for study of quality metrics. So formalizing the process that I was mentioning before, we try to cover a wide set of types of content. We try to at the same time sample let's say if we use the SITI space as characterization, we try to cover that space as well. Then we try to have some very typical compression methods that are used, and then we can start throwing metrics at those and try to study how those metrics compare to formal quality, subjective quality assessments. So that's something that's very interesting, but it's also a large effort to be performed. Okay, that's it. So we have I gave you an overview on MPEG 85 and visual quality assessment. We looked at the CFP activities, we looked at the verification test activities and some constraints that we have on those two, and further activities that we have in 85. Of course, we always welcome participation and also contributions, so we'd be happy to see inputs coming from your groups and from all over the world. That's it from my side. So thank you very much. Thanks for your attention. And I'm, of course, happy to answer questions.